Hi friends, let us understand how to design or devise a mapping technique of analog to digital filter transformation using impulse invariance method. So we will be devising today a method called as impulse invariance method. Now let us first see what will be the steps required in doing that. So the first input to this process will be my transfer function, which is from analog domain. So I write as HA of S. So this is a transfer function in analog domain. Okay, so I write HA. A stands for analog, and because it is in analog, which what will be the domain which I will be working is Laplace, which is S. We'll be giving this as input, and the ultimate output will be H of Z, which is the transfer function in digital domain, right? So I will have a transfer function in analog domain as an input, and I will have a digital domain in as a transfer function as the output. In between, I have to do that mapping. How we will be doing it? In first step, I will obtain H of t, which we call as, let's say, HA of t. How can I do this? I will be applying inverse Laplace transform. So we'll be applying inverse Laplace transform on HA of S to obtain HA of t. Once we obtain that, from this function I will obtain H of NTS. H of NTS is applied, or it's obtained by sampling method. So I'll be applying a sampling method on HA of t, and I will get H of NTS. That means we are replacing t by NTS, where TS is called as sampling period. After getting H of NTS, I will be getting H of Z. How will I get H of Z? I have to apply Z transform. So if I apply Z transform of H of NTS, then I am going to get H of Z. So what we will be doing first, we'll be taking analog transfer function, we'll be applying inverse Laplace transform, then we'll be getting HA of t. After doing sampling, I'll get Hn of TS, and after getting this sampled version, onto which I apply Z transform, and I will get H of Z, which is the transfer function in digital domain. So let us do this method and see whether the three conditions are satisfied by impulse invariance method. So let us consider HA of S, which is, let's say, an all pole filter, and there are in all k poles available. So HA of S goes as k is equal to 1 to n. A of k are constants upon S of S minus p k where pk's are the poles of the transfer function. So this is my given transfer function. Now step 1 is I will apply inverse Laplace transform. So I'll be applying inverse Laplace transform. So I will have Laplace inverse of h a of s, which is nothing but Laplace inverse of summation going from k equals to 1 to n a of k divided by s minus pk. Okay, now how can I write this summation? I can put values of k, so it will be like this: Laplace inverse of a1 upon s minus p1 plus a2 by s minus p2 plus dot 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 plus an upon s minus pn. Okay, now because Laplace is a linear operator, I can split this operator on the addition. That means I can write as Laplace inverse of this quantity plus Laplace inverse of this, and so on and so forth. So I'll write it like that: Laplace inverse of a1 upon s minus p1 plus Laplace inverse of a2 minus upon s minus p2 plus so on till Laplace inverse of an upon s minus pn. Okay, now Laplace, because it's a linear operator, all the constant values will come out of the Laplace operator, and you will get the function as a1 Laplace inverse of 1 upon s minus p1 plus a2 Laplace inverse of 1 upon s minus p2 plus so on for the n values. Now Laplace inverse of 1 upon s minus a, this is just a formula, is e raised to, if it is minus, it will have plus at, okay, u of t. Okay, so this is a Laplace formula. So if you have Laplace inverse, this is just a recall statement from maths. So it's a recall statement from mathematics which says that Laplace inverse of 1 upon s minus a is equal to e raised to at u of t. If it is minus, this will be plus. Okay, apply this on the above formula. You will get a1 e raised to p1 t u of t plus a2 e raised to p2 t u of t plus so on till a n e raised to p n t u of t. Okay, so let us take u of t all common and make it again in terms of summation. So I have summation. Okay, let's say that we started with k, so let's say k is equal to 1 to n. Okay, I have now a k, these are a1 a2 to an, that is a k into e raised to p k of t u of t. Okay, because this is p1 p2 and pn, so it will be pk of t u of t. So this will be my h of t after application of inverse Laplace transform. So this is the first step that we have achieved our h of t. Now we have to go for the next step. Next step states that we have to apply sampling onto this function. So if I apply sampling, then I will replace t by nts in the above formula. Then the function becomes h of nts equals to summation k goes from 1 to n, okay, ak e raised to pk into nts into u of nts. Now, as we have done the sampling, the sampled version of h of n. After this step, I will apply the Z transform. So let us apply Z transform. When I apply Z transform, I am going to get h of z, which is equal to summation n going from minus infinity to plus infinity, okay, h of nts z raised to minus n is the formula. Now, if I put h of nts, from h of nts we can see that it is u of nts, and u is a unit step function which starts from n is equal to 0 and tends to infinity and extends up to infinity, but it starts at n is equal to 0. So this n will be now restricted from 0 to infinity. So my h of z now will look like summation n going from 0 to infinity. I'll substitute the value. So the value will be again a summation. Now the summation of k goes from 1 to n ak e raised to pk of nts. This value will be 1 in this range, so I'll not put that, into z raised to minus n. So now I can interchange the value of summations, because this summation runs on k and this summation runs on n, and they do not have any relation with each other, so I can interchange their positions. So let us interchange their position. So my h of z now will be, let us first write summation with respect to k. So I'll write k is equal to 1 to n, and I'll bring ak also outside because ak is independent of n. Then I'll write the next summation which depends on n. N is equal to 0 to capital to infinity, okay, and we will be putting the rest of the part, which is e raised to pk into nds, okay, to z raised to minus n. So now let us interchange the position of the summations. So as we have interchanged the position of summation, we have brought k variable outside and have kept n inside. Now let us rearrange this term, and now we will get summation k goes from 1 to n ak, okay, and now what we will do is I will keep summation n going from 0 to infinity, okay. Then I'll write it like this, e of pk into ts, and then I'll write z raised to minus 1 the whole raised to n. So what I have done is I have taken n as a common index for both the terms. Now, just for your reference or just as a recall, summation n going from 0 to infinity a raised to n is equal to 1 upon 1 minus a. The series turns out to be 1 upon 1 minus a. Here this is my a. So let us replace. So if I replace, then I will get summation k going from 1 to n ak, and this entity will be now 1 upon 1 minus, now a will be equal to e raised to pk ts into z raised to minus 1, right? Let us bring that AK inside. We will get equals to summation k is going from 1 to n AK divided by 1 minus e raised to pk ts z raised to minus 1. Let us compare this with our previous equation. So let us take our equation number 1 of HA of S. So this is my H of Z. I'll write again H of S where we started from. H of S was summation k going from 1 to n, okay, AK divided by S minus PK, where PK was the poles. Now if I compare both the equations, okay, they look very similar, where we have the poles, or we have pole at here we have pole at pk's, whereas here we have the pole at e raised to pk ts. So if I see the poles, the pole will be equal to s equals to pk, and here if I put that, then the pole becomes, and the pole over there is z e raised to pk into ts. So I can replace pk by e raised to s, and I get es raised to ts. So I get the relation between z and the s as z is equal to e raised to s ts. So that is the relation between the two transfer function. So what I have to do in the transfer function is, if I wanted to transfer from h of s to h of z, then I have to replace all my poles from s minus pk to e raised to pk, okay, with the sampling period ts. So just need to replace the pole values, and I will get the relation as z is equal to e raised to sts. Now let us see whether this z is equal to sts mapping satisfies our criteria. So let us follow the criteria for mapping. So let us verify our criteria for mapping. Okay, the criteria for mapping in z is equal to e raised to sti, right, which is sampling period. Now what I'll do is, I will consider, or I will put the I'll put s as equal to sigma plus j omega, where omega is a analog frequency, and z as equal to r e raised to j omega, where omega is a radian frequency. So if I replace it, I will get r e raised to j omega for z, and I will get e raised to sigma plus j omega, okay, into t. So if let us solve it, e raised to j omega equals to e raised to sigma t into e raised to j omega t, right? So if you take the if I compare the real parts, so let us compare real and imaginary parts. So if we compare the real and imaginary part, then r becomes equals to e raised to sigma t, and omega becomes equals to omega into t. So this is what my equations for r and omega comes out to be. Now with this sigma t and omega t, let us see the mapping. So for mapping, let us use r e raised to sigma t. If I use r e raised to sigma t, then for, let me draw the s plane and the z plane. So in the z plane, I will have a unit circle whereas in the S plane I will have I'm extremely sorry, this is j omega and this is sigma, and this is a radius 1 and you have omega. Now if suppose I place a pole on left hand side of the S plane, that this becomes minus sigma. If I put minus sigma over here, it becomes e raised to minus sigma into t. Okay, e raised to minus sigma ts will all be mapped inside the unit circle. Okay, so if you put sigma less than less than 0, we say like this, sigma is less than 0. So if I put sigma less than 0, then r will be less than 1. Okay, because we are going to get the values in terms of points, so that all poles will get mapped onto the inside the unit circle. So for a causal system where the poles are on the RHS will all LHS will all get mapped inside the unit circle in the Z transform, so that criteria is satisfied. Now for sigma equals to 0, that means all the poles which are on the j omega axis, when sigma is equal to 0, then if I put r becomes equals to e raised to 0, which is nothing but 1. So all the poles on the imaginary axis will get mapped onto the unit circle. So the second criteria, that the system to be the poles which are on the j omega axis are mapped onto the unit circle, so that is also satisfied. If I put sigma greater than 0, that means on the positive side, that means poles are somewhere around over here, then r will be greater than 1. That means that all poles on this side will be mapped outside the unit circle. So that is how the mapping of poles are occurring. That means if I have a stable S domain or an analog filter, then using IIM method, that is replacing all poles by e raised to est, we can actually put all the poles inside. The stable filter of analog can be mapped onto a stable filter in digital circuits. So that is how we verify from this signal, from this equation. Now let us come to this equation and see what does this equation gives us the information about. Now let us determine what this equation tells us. So I will write that equation as omega is equal to capital Omega into Ts, where Ts shows the sampling. Okay, it determines that the frequency is sampled. The discrete frequency will be sampling of this sampled by a frequency of Ts. So this omega is having a range of minus infinity to plus infinity, whereas this omega is having a value which is from minus pi to pi. So what will happen is too many ranges of frequencies in omega will mapped onto a small omega system. So there will be too many values of frequencies in the omega domain that will get mapped into minus pi to pi range. So it is impossible for us to actually have each frequency component of analog circuit to mapped onto discrete circuit. So there will be overlapping of frequencies. That is, the technical name of overlapping of frequencies is aliasing, and the aliasing is a result from sampling. So we have performed sampling of frequency which results into aliasing, and aliasing causes overlapping of frequencies in impulse invariance method. So that is the only disadvantage of an impulse invariance method, which can be avoided to a greater extent by using a proper sampling frequency. So this is how we find that impulse invariance method satisfy all the criteria for mapping an analog filter to a digital filter. Thank you.